So hello and welcome to the How the Hive Came to Be webinar. So this is the second webinar of the series. The previous one touched more around the history of eBPF. And in this one, we want to do a technical deep dive of eBPF. First things first, a couple of housekeeping and logistics items. So all attendees in the webinar, they are muted when they're joining. And if you have questions, please send them to the Zoom chat. And at the end of the series, we're doing Q&A. And also to all the registrants, the recording will be available afterwards as well. So a little bit about myself. So I'm Daniel Borkmann. I've been involved in eBPF and in Cilium since the very early days, helped with its creation. And these days I'm in the Cilium data path team and leading the development there. Also hacking on the kernel on eBPF, co-maintaining it. So eBPF in a nutshell, what is it? It really is a framework to extend the OS kernel. So it's a general purpose engine which has a minimal instruction set, and it allows for running programs, user-defined programs in the kernel in order to customize its behavior. And you can customize it without, changing the kernel source code, without upstreaming your specific code that maybe solves something specific for you. And you can change that behavior without having to reboot the kernel, and in particular without crashing the kernel in case you have bugs in your program. There are a number of use cases around eBPF. So far, the biggest ones, there are always new use cases evolving. The older it, the more people use it, but the biggest use cases are in networking security and tracing. So networking, we see it being used specifically for denial of service protection, for load balancing, firewalling, implementing gateways, for reducing the attack surface of the host system itself, but also to customize the networking stack. For example, when you have Kubernetes and you have a CNI and Cilium as one of them, it uses BPF underneath, and then you can do all the forwarding with BPF and implement custom behavior there. Same for security, so you can gain introspection to your system, you can implement security enforcement, and more generally, also it's very heavily used in tracing and observability. In general, when you write an application, it typically, orchestrates the BPF code. So it typically ships with the user space component, maybe written in Golang. And it has a portion which is the BPF code itself that gets compiled and loaded into a kernel through a loader. The application itself basically orchestrates that, and it also interacts through shared memory with the BPF program that is sitting in the kernel to extract data out of it or to push data into it. So BPF can really be seen as a new type of software if you compare this to traditional user applications or the kernel itself. So user applications in kernel, they both run in a task, in either kernel thread or user thread. BPF is based on events in order to trigger its execution. Both your user space application, but also BPF, they are user defined. The kernel itself is not, because that's what the whole kernel community implements and that everybody runs, right? So it's really static. And while in user space, your application, the security depends on, however you implement it or whatever tools you use to make sure that it may be secure. In the case of the kernel, you don't have any security guarantees. So like when there's a kernel bug and it's, it can crash your system, it can destabilize it. In the case of BPF, even though it is running in the kernel, it is going through a verifier that makes sure there's safety around it, and you have like a seatbelt in that sense. In case of a failure in your user space application, when you have an invalid memory access, for example, your application aborts, triggers a segfault, for example, your kernel, the kernel will panic, and BPF, there's no such option. So it either has to throw an error message but it cannot destabilize the system, right? The resource access in the case of your user space application, well, it has to call, so it has to execute system calls in order to go into the kernel and, access hardware in a safe manner. The kernel can, of course, use it directly. And in case of BPF, you have restricted access to this through BPF helpers that call into kernel code, which then can access those resources. The state model of BPF. So BPF gets loaded into the kernel from user space and it's enabled. So it's basically off CPU at this point. Only when an event fires, it gets active on the CPU and it's typically run to completion. There is a possibility where BPF program can sleep when it's being preempted. One example is tracing programs where they want to access user memory and it's not immediately available. But so then they will go back to kernel at a later point. The BPF program can transition into kernel through the BPF helpers. You can also spin lock. So there's an option where you have access to spin locks from BPF. So in 2022, there are lots of moving components to orchestrate BPF, both in user space and in kernel space. In user space, you have your application that holds, as I mentioned earlier, the program. It gets compiled into bytecode. That has to be loaded into the kernel through a loader. There's BPF type format, which helps with the verification and the description of data structures. And it's also used by the verifier. And the verifier makes sure it's safe. There's a JIT component, a so-called just-in-time compiler, which translates this into the BPF program into native machine code. There's the whole runtime, which provides the attachment points, different BPF helpers that you can use, and facilities to share data with your user space, like back to user space, to the application. For example, the application can either push data into BPF or it can extract it. There are also ring buffers, for example, the BPF ring buffer, the perf ring buffer, to push events into the user buffer, into the user application. But you can also extract statistics or stacks for tracing in particular, which is relevant there. So yeah, and that's not even like the complete picture. So it really is a simplified version of it. In the case of tracing, you have different options to attach BPF programs. I've listed some of them here. And then we also have networking. So there's really a lot of components, like you can attach to core networking in different areas. You can implement congestion control with BPF or get L7 visibility and so on. In case of security, again, you can implement LSMs there, so you can attach to this. You can also attach, again, for the observability piece to different, K-probes or F-entry, F-exit events, for example. So it like the boundaries between security here and tracing that I mentioned earlier are not strictly fixed. Same for networking, right? So yeah, BPF as a new type of software, it can, it can replace a lot of the classic infrastructure that we know that has been developed 20, 15 years ago. And for example, in the case of networking, a lot of use cases, they center around, moving from IP tables, IPVS to BPF because you gain more efficiency, more flexibility. Same with tracing. So like the traditional tools that have been used, you can gain much more visibility into the kernel through BPF because of its flexibility in one area that is also coming up more and more security. So like all this infrastructure is centered around BPF as a common denominator for all of them. And you see like various projects on top. So they may not replace all these classic infrastructure pieces one-to-one, but rather they can adapt and integrate more in a better way to today's requirements. For example, just think about Kubernetes. So you can move context from Kubernetes pods, for example, into BPF, and because of that, you get much more flexibility that you otherwise would not get with those more classic tooling. So yeah, so in this talk, I want to go to the journey from the C program all the way to the BPF runtime. How does it look like step by step? So typically you have a C program that gets pushed into a compiler which has a BPF backend, which can be LLVM or GCC, then generates an object file that gets pushed into a loader. The loader prepares all the data from it, and then it gets pushed into the kernel. So just having here like a toy C program for one of the networking hooks, in this case XTP, and I'm just, it's a completely stupid and silly program. It just implements a kill switch where you either drop all the traffic or pass all the traffic to the stack. If you compile this with LLVM, you can dump the intermediate representation from it. It's quite interesting if you want to take a look at this. So LLVM basically has a couple of different front ends, and all of the, from the front ends, you can generate an intermediate representation, which is the same for all of them. And from there, you have different backends, for example, for x86, for ARM64, but also for BPF. And this is how it looks when you compile it when you dump the intermediate representation for BPF. So you have a couple of information about the program itself, about the needs regarding the program data, for example, the endianness, the integer alignments, the integer widths, they are encoded in here, the natural stack alignment, and so on. But you also have aggregate type definitions that you use in your program. In this case, it's the XTP structure, like the context that you pass into the program. You have a bunch of information around the global data, global variables in the different sections. And then you have the XTP entry function that I showed earlier in C. This is being translated here into the instructions for the intermediate representation. And last but not least, there are some attributes that are relevant for the function itself. And then as a next step, when you convert this from the intermediate representation to basically BPF instructions, what you can see here in the resulting object file that the compiler generates, you can dump this through LLVM object dump or other tooling. You can see here that the object file, it's a standardized ELF format, and it has different sections. Those sections, they can contain program code, they can contain data, like global data that go into different BSS section or things like that. And it has a symbol table. And if you look, for example, into the program section, those are the opcodes. They're here and they are disassembled on the side. So you can see here, this is what LLVM emitted, and this is what then later is being loaded into the kernel. So you have here the actual opcodes for BPF instructions. So both LLVM and GCC support this as a backend. LLVM has been the first compiler to officially get this merged upstream. GCC came way later, and it's now catching up to have like feature complete, to be feature complete compared to LLVM. But in general, the main development happens around LLVM these days. It has a couple of targets for BPF, which is interesting. So there's like different endianness. So you have host endianness, the default, of course, and there's big and little endian. So big endian is typically what you have for architectures such as S390, where the CPU operates in big endian mode. You have little endian, which is for x86, of course, and other major architectures. And this allows to also cross-compile if needed, right? And it supports a different set of instruction extensions for BPF as well. So you can see this mCPU argument. This can have different versions, and the base version, the generic set, is the most generic, which will work on all the kernels. But there are also a bunch of extensions we added in the BPF in a runtime inside the Linux kernel, for example, to get different jump 64 variants as instructions, or the set of jump 32 pendants, and also ALU 32 extensions. So you can select this, what you want to compile. You can also use a probe, which will probe the underlying kernel and then will automatically select the right things. How do the eBPF instructions look? So you can see the bytecode format here. It contains of an opcode, destination source register, a offset, and an immediate. So the opcode itself, it will describe different instruction classes, then sizes for the memory operations that you do, for example, on a like a single byte or a half word or a double word. This is, for example, relevant for the load store instructions that we have in BPF. The source encodings, so for example, an instruction can hold an immediate, as you can see here, but it can also be register based, and this is to basically toggle between those two. And in general, like the instructions, in particular for jump, ALU, and move, they are for both 64 bits and also 32-bit available as classes. The instruction is in general 64-bit wide, and there are some exceptions where you have like a double instruction with 128 bits. And again, the encoding, in particular for the offset immediate, is either little endian or big endian, depending on your underlying CPU. So you don't have to convert to one format. And in general, those instructions, they are designed to map to native opcodes for all the major 64-bit architectures in particular. And the goal here is, in particular, that for the just-in-time compiler, you can map these, let's say, almost one-to-one to native machine code, right? Not all of the instructions, they will map to that, but to optimize for the most frequent cases at least. And there have been several instruction extensions. So I mentioned the jump extensions already. There are also atomic extensions, so that you can use atomics for memory operations like compare exchange. And there are a couple of in-kernel only pseudo instructions that are not exposed to user space, but for example in tracing, you have a load where like a load to memory, for example, from some kernel structure where you do not fault if there's an exception triggered. You have a zero extension in instruction, which is inserted to help just-in-time compilers where there's no implicit zero extension. And there's also a no speculation instruction. For example, on x86, this will translate to an L-fence. I have a small program here just to show you how the instruction encoding looks like in practice. So this small program will load the run immediate value of 1 as a return. It will load from a map address. In this case, it's a global data load, and it will store a value into the map, and then it will exit, right? So how does the encoding look like? So you can see the opcode is in this case B7. It's an 64-bit instruction. It's a move, and it loads this from an immediate value. You can see the destination in this case is R0, the register 0, and the source is fixed because we're not in a register-based operation, but rather on an immediate-based. The offset is fixed, so that must be fixed in this case, and the immediate value is 1, and you can see that's encoded in little endian. The next case, so we have this double instruction. That's what I mentioned with like earlier. It's a 2 instruction write, and this is a load of a 64-bit value into a register. And it's this time register 1. The offset again is fixed, and here you see the lower half of the 64-bit value that we want to load, and the second part of the instruction has all the opcode, destination, and offset, like the registers and offset fixed to 0, and then it holds the upper part of the 64-bit value. In general, this is in this case a memory address that we want to load from in this case again from a BPF map. And now we have a store instruction. So we want to store a double word, so a 64-bit value, into memory. So we can see the destination in this case is R1, which holds the memory address. And the offset, in this case we have an offset, it's 8. and the immediate value, again encoded in little endian. Last but not least, we have an exit instruction, and the rest here has to be fixed to 0. So yeah, that's how the instruction look like. Now moving over to the eBPF runtime. So it has some fixed conventions that hold true across all the architectures. We have register R0 to R10 available in our eBPF runtime. R10 is a read-only register, which can not be written to from eBPF, like from a user program itself. It holds a frame pointer, and this is needed for stack read and writes. There's R0, that's typically your turn value. R1 to R5, they are caller saved registers, and they are typically used to pass arguments to BPF helper functions or to other BPF functions. So when you have function calls. And then again, you have R6 to R9. They are callly saved, and so they are preserved across those function calls. Those registers, they're generally 64-bit wide, also for 32-bit architectures. So when you run on ARM32, it's still the registers in BPF, they are 64-bit wide, but they can have 32-bit sub-registers. And those are 0 extended. You can have a private program stack up to 512 bytes. If you don't use it, it's not allocated. And as an entry, you pass in some so-called context, where the BPF program gets interesting data that it needs to operate from the kernel. It's like a structure that the kernel prepares, and then the pointer to it is passed into the BPF program into R1 as an argument. And then once the BPF program completes, it passes a exit value, in this case R0, back to the kernel. And then in pseudocode, you can think of it like this, right? And then the kernel can do something with the exit code, with this verdict in the end. So going to the BPF verifier. So the BPF verifier is essentially a static code analyzer. It has to walk an in-kernel copy of the BPF program that is basically passed down to the kernel through a BPF system call. And it must ensure a couple of things, for example, that the program always terminates. So there's a depth first search traversal to make sure the program is a DIG. It has to prevent unbounded loops. Otherwise, it wouldn't terminate, of course. And it has to prevent malformed jumps as well, so you don't jump to any particular address in the kernel somewhere. It has to ensure also memory safety, so you cannot access memory out of bounds, or it prevents use of the free bugs for the objects that you use inside BPF that you get from BPF helpers, for example. And especially for unprivileged, it also mitigates vulnerabilities from the underlying hardware, at least like a large set of them that are known. The verifier needs to ensure type safety so that you don't have type confusion bugs. And there's also BTF, the BPF type format, and it helps in verification around certain access of kernel data structures, for example, as well during the verification process. Verifier also has to prevent hardware exceptions. Best example here is division by 0. It will reject it when it's known at verification time, but sometimes it's not known, then it has to rewrite it, like those instructions. The verifier works by simulating all execution paths of the program. So it follows the control flow graph, and for each instruction, it computes the set of possible states. Like that concerns both the register set that we have, R0 to R10, and the stack. And it performs the safety checks based on the state it collected and the current instruction. It also tracks, register spill fills that are to and from the stack, like from that private stack of the BPF program. If there are back edges in the control flow graph, then the verifier needs to, brute force simulate all of them. So it like bounded loops, they are supported up to a certain limit. And because of that, or like in general, because it has to go through all the possible paths of the program, the verifier has to deal with the potentially large number of states. So there's path pruning logic included in the verifier, where the verifier looks at previous program paths that have been taken and that have passed the verification, and whether my current path of the verification, if there's an equivalence of the state, and whether it would be safe to exit early. So yeah, and what helps in this case that is implemented in the kernel is function by function verification. So it verifies them piece by piece and then only later on checks the inputs and the outputs. There's a precision tracking for unknown scalars. So it only goes back and figures out whether the scalar is actually like a constant if it really has to. For example, when you have a length that you pass to a BPF helper call, for example, then we really need to know because you need to verify whether something is out of bounds or not. And the verifier will terminate and reject when it crosses a certain complexity threshold, we call it. So in the kernel, it's 1 million instructions. After that, it will give up and say, okay, it's too complex, it takes too long. The register state, it's a simplified version that I put here, but basically a BPF register in the simulation that the verifier is doing has a certain type. It can, for example, be an unknown, completely unknown type, or like a scalar type, or some pointer type that can be null or non-null. It has an ID in order to propagate state back and forth, and a fixed offset, a unknown offset. So that's, we call it a tri-state number. So it represents basically knowledge of known and unknown bits combined. And it has a number of bounds, so 64-bit and 32 bounds, min, maximum, and signed, unsigned. So it really has to track a lot of information. One thing that is interesting are tri-state numbers. They essentially contain a value and the mask. So the value, if it's 0 or 1, it represents actual known bits. And if the value is 0, and the mask is 1, it's an unknown bit, right? So for example, if you take 010x, basically the value here is 0100, and there's a mask where you have bit 1. And this essentially represents a set of these two numbers, 4 and 5. And when everything is unknown in this small example with those 4 bits, all of the masks are 1, all the bits there are 1, and they basically then represent 0 to 15. The tri-state numbers and bounds, as we saw earlier, there are also minimum and maximum bounds. They are needed both because those bounds, they actually refine the set from the tri-state numbers, because those alone, they are less precise than what you could get with the bounds in combination. You can also do arithmetic operations, what you can see here in this example, and the result will be, less precise, but it's accepted, you know. So what you can see here, the 23 doesn't belong into the set, but yeah, close enough. Worse, like it's worse in the case of multiplication, for example, right? And there has been research from academia that has actually improved and like the multiplication algorithm and made the resulting set more precise than it used to be, for example. Just to give a toy example around how the verification looks like. So I have here a small program and we have a structure. The structure has an index, it has a value, and it contains an array. And we want to write the negated value into that array at a given index, right? And that structure is part of a map value. So that's memory that is available to the BPF program. How does it look? So so we just assume in this case, for the sake of simplicity, that the register R0 points to the structure, like to that map value. And initially in register R1, we load the index itself. So it's a byte load. And in register R2, we load the value that we want to later on store. In register R0, we add the offset to the start of the array. And then we calculate the index. So we have to multiply the loaded index with the, with the width of the array field, in this case, 4 bytes. And then we add this later on to the map pointer to the map value pointer. We negate the value that we want to store, and then we actually do the store. And now, like, I want to go through this. How does it look from the verifier perspective, right? That's quite interesting. So our 0 points to the map value. What we do know is that the value size is 1032 bytes. And now we load from the map value the index. So given it is a 1 byte load, the maximum value can be 255. But everything else, that's the tri-state number, is unknown, right? So you see the value and here the mask. So all the bits from the mask are unknown in this case because we don't know anything more. Then again, we load the value. It's a 4 byte load. So the maximum value it can hold is the maximum that U32 can hold in general. And all the bits are unknown again. Next up, we add the map to the map pointer, to the map value pointer, we add the offset to the start of the array. So in this case, the offset it holds is 8. And now we multiply now we calculate the actual index by multiplying with the array slot size. So the Umax value changes in this case, as well as the unknown bits it can hold. We add this to the map value pointer. So this information propagates there. And here we negate the value that we later on want to store. So here are no particular constraints. And then we store it. And we know it's safe to store it because it fits exactly into the map value memory. There's no out of bound access, so it's safe. So that's roughly how the verifier works in very simplified version. So there are a number of challenges with that. So especially when the verifier, or like when BPF is exposed to non-root, these days this is disabled by default, but it has been at least an attractive target for exploitation. Given the growing complexity of the verifier, the community is large, community is growing, and more contributors are there as well. So potentially bugs could slip in. And you know, the programmability of BPF, it gives a lot of power, a lot of flexibility, but this can potentially be abused to mitigate, like to bypass mitigation. So in this case, especially Spectre, right? The reasoning about the verifier correctness is really non-trivial. So you saw just a tiny example in here. There only have a few things here only have been partial formally verified, like the tri-state numbers. There has been formal verification around the just-in-time compilers, but it's non-trivial, especially with the Spectre mitigations, which are applied for unprivileged, you know, to avoid leaking data under speculation. There are occasions where valid programs they get rejected because, you know, there are new optimizations in LLVM. The verifier doesn't understand them yet, so it needs to track the state. There's a stable API for BPF programs. It has some limitations, especially on tracing, where the kernel can change anytime when you inspect kernel data structures. But in general, if you have BPF networking programs, for example, you don't want them to break on your kernel upgrade. So that needs to be taken into consideration as well from a verifier point of view, that those programs have to continue to pass as well. And there are performance versus security considerations. So the verification of complex programs must be efficient. Like if it takes 2 minutes to come to a conclusion whether it's safe or not, it's not practical. And mitigations for, let's say, hardware bugs, for example, they must also be practical because performance is still crucial for BPF. Also safety, of course, both have to play in there. One thing that has been, you know, like a complex area are like the 32 and 64-bit operations, ALU and you know, the bound tracking there. So that made the verifier quite complex. And again, like the active development from the community, you can see the number of lines of code over the years. So it's been growing quite a bit. Now coming to BPF type format, or BTF. So you shouldn't regard it as a debugging format, but really rather as a metadata format for BPF, but also could be used beyond that. So it describes types, it describes relocation, it describes also source code. If you look at it from a kernel point of view, like if you compile the kernel with the bug data, it has roughly, let's say, 124 megabyte. It has been measured in one of the cases. And with the BTF, it's a much more efficient data format where you can store type data, and it can shrink down, in this case, to 1.5 megabyte only. BTF in general has become an essential part for BPF today. And the kernel comes with the built-in BTF blob of itself. So that's basically baked into the kernel at build time. And when you run the kernel, this BTF blob is exposed under sysfs. And it's trusted information because it has been built into the kernel. Nobody can change it. It's read-only. And it can be used during verification. So it can really help the verifier with coming to a certain conclusion. For example, when you walk data structures in the area of tracing, for example, or when you need to match function signatures, BTF is a big help here because it describes those. And it's used by BPF loaders. I didn't talk much about loaders, but it's used there to process compile once, run everywhere relocations. For example, when between kernel versions, certain offsets of the structures change, this can be fixed up automatically because you get the whole BTF image from the running kernel, and then the loader can fix this up transparently without the BPF program author having to be aware of it. And the BPF programs themselves, they also come with a BPF blob. In this case, this is untrusted and has to be verified. So there's a verifier to check the sanity of the BTF information in the kernel. And that blob stays associated with the BPF program. And it's also used during verification. For example, BPF programs, they can have BPF spin logs, timers, global data, and that information is baked into BTF and helps in the verification process along with that. Also, there's it holds source code information. We call this BTF line info that is also stored in kernel. And when users want to dump with BPF tool, for example, what programs are loaded in the kernel, they can dump the programs along with the source code. So they get full introspection what's going on. Just as a toy example, what you can see here is a simple C data structure. And if you do the BTF conversion, this is how it looks as pretty printed BTF. So you can see there are like basic types described. They can have a name, they have different size, and they have a size, and they have different information in terms of how many, like how wide the data structure is, whether it's signed or not signed, or whether it's an aggregate type, and so on and so forth. So the verifier actually, if you dump the program after loading, you will see that it's a little bit different than what you originally loaded, because the verifier performs certain rewrites as part of the program. They still, of course, have to be semantically equivalent. So, for example, when you access kernel objects or BPF objects, such as BPF maps in user space, you don't know the BPF maps kernel address, of course. So you put in, or the BPF loader encodes the file descriptor. And then later on the verifier in the kernel, it retrieves the BPF map and it replaces it with the actual address, which is what you also saw in this example earlier with the double load instruction that I showed. There are also other things. For example, you can address in a read-only manner kernel symbol addresses through BTF, for example. The verifier also rewrites programs in order to prevent hardware exceptions or hardware bugs. Best example is the division by zero case when it cannot be statically analyzed, or it helps the just-in-time compiler to insert zero extension pseudo instructions. In some cases, we try to eliminate speculation where possible by rewriting known constants with actual, constant instructions. For example, like a load of an immediate. the verifier, like especially for unprivileged, we need to protect against spectre attacks. So it also implements masking there. So there are some details in other talks you can refer to that I did on that. Another job of the verifier is to, because performance is crucial for BPF, and to gain a better execution efficiency, it tries to inline certain BPF helper calls, such as map lookups, or if you retrieve the jiffies from the kernel, the jiffy value, or other things, right? It tries to transform indirect calls to direct calls because they are much faster, and you get a better, you don't get the overhead of, for example, red booleans, which are there to mitigate some of the spectre bugs. And last but not least, there are also cases where the verifier prevents JIT spraying attacks, especially for unprivileged. Again, how does it look like in practice? So when you have user program, that user program has a division which cannot be verified, the verifier will rewrite it. In this case, for example, if the value of the divisor is not 0, it will actually do the division, but if it is 0, it will zero out the destination register and then skip the division in order to not trigger a hardware exception. Similar with the modular operation. So in this case, if the divisor is 0, it will then basically put it into an invalid state. And this is nothing new. So this is also done, if you look into the ARM architecture manual, it's also done there, for example. So you not all architectures will throw an exception in this case. And for BPFs specifically, we can also not throw an exception because, for example, consider the case where a BPF program does a function call, and there in that function call, in those BPF instructions, you would have a division by 0. Then what do you do, right? If you return with an error, well, that's maybe not what the verifier expects, because it expects maybe that a pointer is returned. So there you would otherwise bypass the verifier simulation if you don't do that. Turning indirect calls into direct ones. So that's another example. If the BPF program does a helper call, for example, to delete the map element, but there are also various other cases, the implementation of it dispatches into the actual BPF map implementation, and that's an indirect call. And if the verifier like in most of the cases, it can turn this into a direct call of the actual map implementation under the constraints that the arguments from all the different paths are still the same. JIT constant blinding, I put this in here as a funny example as well. That is interesting. If a user program loads constants, in the end, they end up in executable memory in the kernel. So if you have other kernel bugs elsewhere that could trigger a jump to this, then it's pretty bad from a security point of view, right? For the untrusted programs. And in this case, it will blind out by XORing this with a random number and then actually turning the immediate base load into a register based load. And this is how it looks after the just-in-time compilation. And yeah, this way it makes it ineffective. So coming to the BPF JITs, because I was just talking about it, the basic purpose is basically to move the post-verifier BPF program to native machine code. So you might ask, why not interpreter, right? So really for the vast majority of users these days in distributions, it's compiled out of the kernel. So there's no BPF interpreter in the kernel anymore. It's not only significantly slower, but in general, any interpreter in the kernel, not just BPF interpreter, is also a security risk. Why? Because in the first Spectre attacks, when they came out, the attackers were able to leak host memory from a KVM guest because it was able to execute code and jump speculatively to the interpreter. So yeah, that's why we compile it out, and the just-in-time compiler is used. So it stores instructions into a read-only executable image, and all the relevant 64-bit and 32-bit architectures as well, they have BPF JITs today. And x86, ARM64, MIPS, PowerPC, RISC-V, they're all in a pretty good shape. So you can use it. And JIT compiler are really an optimization function. So you want to optimize so your cost is basically the size of the resulting image. And that's what needs to be minimized in order to be efficient for the CPU's instruction cache that is underneath it. For example, on x86, the JIT compiler is usually doing multiple passes in order to shrink the image further and further if possible. And yeah, I mentioned the constant blinding, so that is done in the pre-JIT phase, but then it's really common for all the JITs and doesn't need to be implemented JIT by JIT. How does it look? If you have this toy example again, with this global data here, BPF instructions on the left side, they get converted to x86 instructions. I colored them into the, like with the same color. What you can see here is that we converted 40 bytes of BPF instruction into just 24 bytes of native opcode. And then you also have to consider the BPF instructions. If they would be interpreted, that's another big overhead, right? And in this case, it's executed directly. There are also prolog epilogue, and it contains a couple of things like setting up frame pointer and so on. So now we covered all the phases, and the last one is the BPF hooks. So I took as one example, there are many hooks, as I mentioned earlier, XDP. So XDP is really about networking performance. So back in, I would say like 2016, 2015, 16, there was DPDK on the rise, and it was really hyped. And the general consensus was, well, the Linux kernel data plane is too slow. So there are performance requirements with the 10, 40, 100 gigabit NICs coming up. And around the Linux kernel, there are optimizations done by the whole community, but they usually center around local delivery, local applications. But around routing, it's really hard to do. Consider all the corner cases that the stack need to handle and so on. So back at the NetDevConf, actually we had hallway discussion and we were just joking, well, why don't you just put BPF into the driver layer? And it then actually materialized, and some folks from the networking community came up with the concept. And that's what we call XDP today, right? Running BPF from the driver layer in the networking stack. And the other thing is not only too slow, but the other argument, well, it's also not flexible enough, right? So back then, the existing facilities like TC, OVS, NetFilter, they had also partially overlapping functionality, but they kind of allowed to program the data path, but then also not really, because the data path, in the sense of those frameworks, they need to know what you want to do, because that's like the building blocks they had, right? Consider this in contrast to BPF, because in BPF you can create as a user the data path instead. The kernel doesn't have to be aware of your specific use case that you want to solve, right? And there's also no need to upstream that specific code that you have and then wait until all the distributions have it. And there's really a short feedback loop from users to alter the kernel behavior, which is not possible before that. There are many use cases that you can imagine with XDP, like running a BPF program inside the network driver on the receive path. What can you do? Load balancing, DDoS protection. You can implement gateways in BPF, for example, to convert from IPv4 to IPv6 or vice versa, right? When moving packets into your cluster. You can implement firewalling. Another case, which is maybe less obvious, stack hardening in the upper network stack. If it has like a packet of dev type scenario, you can drop those packets directly from the XDP layer without, where you can then plan to upgrade your kernel at a later stage without burning fires. You can implement observability, intrusion detection systems, or like custom encapsulation that the network stack is not aware of. Why exactly is XDP faster? Because in this case, really the mantra is less is more. So XDP is a thin layer at the earliest possible point in the network stack. So that's inside the driver's receive path, and before the driver actually allocated the socket buffers, like the main packet representation, the network stack, before it populated them, and therefore it also runs before it tries to aggregate them in the GRO layer, or before net filter IP tables, and so on and so forth. So really at the earliest possible point before the stack is doing anything with them. And BPF in this case operates directly on the received packet pages. So it can load the data from it, it can write into it, and so on. And there you can implement your data path, implement encap, decaps, and so on. And then the BPF program has a return code, and in this case, the verdict decides whether to drop the packet, whether to forward it, for example, to push it back out the same or a different NIC, or to pass it up to the stack because it's maybe for a local application. And if you really need more features, or if you have to push your packet through like into local containers, then you can push it up the stack and maybe let, instead of XDP, TC BPF hook handle it, because there you can operate on aggregated SKPs. And TC has an ingress and egress hook. But for those use cases that I mentioned earlier, XDP is really perfect. And if you compare this XDP performance to DBDK, this is from a paper that we did some years ago, especially when you push out the packet the same NIC, you get close to DBDK performance. And if you look at the CPU utilization, often case in DBDK that it's often the case that you need to busy poll from the user space, so you burn a lot of CPU cycles to be able to process a high number of packets. In case of the regular Linux stack, if you have a high packet load, your CPU usage goes to close to 100% quite quickly because of all the per packet overhead that the network stack has. But then if you attach your program to XDP and do an early drop there, it can sustain a much higher rate, which the regular Linux kernel stack wouldn't be able to. There are also other benefits to XDP because thanks to BPF, also other parts of the stack can be reused. So they are not bypassed, but you can reuse your FRR for routing, for neighbor management, and BPF just does a FIP lookup into the kernel routing table to see where to send the packet to, right? So it can access this table, access kernel infrastructure that already is existing from the BPF program. Then you also reuse the same drivers. So they're upstream drivers, or you can reuse all the device management that you have with IPROUT2 and other tooling. You don't need an EVE tool. There's nothing that needs to be recreated or reinvented. And there's also no need for custom out-of-tree TCP IP stacks, right? Because it's just there. You can just push the packet up to the stack. And then again, there's no need for actual bypass. So XDP, it basically piggybacks on the existing kernel's NAPI mechanism, which is which is polling the driver for packets to batch them and to process them there in the software interrupt case. And it doesn't burn CPU cycles as with busy polling. You can do this if you want, but by default, that's not the case. And because of this, you gain CPU cycles back, and you can also co-locate other workloads on that machine that is processing XDP packets because you can, right? And XDP also allows for atomic swapping of BPF programs without any traffic disruption. So you don't need to move your NIC, you don't need to set your NIC down and reinstall and put it back up. It's just there atomically. So the packet stays in the kernel, and because of that, you can, if it's for local delivery, you can deliver it directly to the networking stack to a local socket as is. And it also has the same security model as the rest of the kernel because it runs in the kernel. And it's easy to set up, and it's available with all the distributions, and most of the major drivers from 10 gig plus have it. And the other important thing, which, for example, DBDK doesn't have, is you're still with the safety belt when writing BPF programs because of the verifier that they went through in length earlier. So to give you an example around load balancing. So in Cilium, we have an XDP-based layer 4 load balancer, and we recently had an interesting user story from a website called, I think, Zesnam. It's like a Czech website, which is a search engine provider. which is quite popular in Czech Republic. And they actually went to the journey from, they initially had hardware load balancers. They in-house, they have a couple of Kubernetes clusters, and they've been using F5 hardware load balancers. And they moved from there to more of the traditional software load balancers, because they run, especially during COVID time, into supply chain issues on the one hand, and on the other hand also increased traffic, because at lockdown people were at home, were searching, browsing the internet and so on. So they received a lot more requests than usual. And then they decided to switch to commodity, to commodity hardware with IPv6-based load balancing, right? And later on they saw that in the case of Cilium, they implemented XTP-based load balancing, and they tried this out to, as a drop-in replacement for the IPv6. And it's really interesting what happened. So when they pushed this into production on a single node for testing, XTP was able to sustain at network packets per second at a much higher rate than IPv6. Here you can see the production numbers where they took in XTP and then they moved it back out, because from testing, and moved back to their old IPv6 system just for comparison. And it's really nicely visible here. And especially the other thing that was surprising to them is the CPU overhead. So XTP, in this case, because the rate was not that high that came in, had really low CPU overhead compared to IPv6. So when you move back to IPv6, the CPU load increased significantly. And last but not least, the last example I want to bring in here before I close the session is Katran as a load balancer. So this is basically the journey from Facebook. So they had really like a similar journey, as I mentioned earlier, from hardware moving to IPv6 and then to XTP. They are actually the first ever production user of XTP. So they implemented the load balancing on their side through that framework with BPF. And given them like the costs they saved because of this, they were able to co-locate other workloads on their load balancer machines, right? And actually since May 2017, all the packets, all the traffic to facebook.com has been processed by BPF and XTP, which is super cool. It's really battle tested. And what you can see here on the right side was the packet per second. So they were able to sustain up to 10x higher rate than with the IPv6 they used before. So yeah, that's it. That was the journey from the C program all the way to attaching BPF programs and running them on the XTP. That was just one example, but just to give you a picture of this whole journey. And with that, I'm closing my session. Please make sure there's another in this How the Hive Came to Be series, another session on September 14th by Joe Stringer, where we talk more about Cilium as a particular eBPF use case. And also to mention eBPF Summit that is coming up end of September. So please make sure to register to not miss out on all the great talks and user stories that we have there. The lineup will be there in shortly. And yeah, with that, I want to open up for question, and thank you for the attention. So if you have any questions, please let me know. Happy to answer. Looks like there are no questions. So if you have any questions at a later point, please contact me also on Slack. I'm in the Cilium community Slack, and I'm happy to answer anything that is coming up there. Awesome. So that's it. Thanks a lot.
Daniel, it actually looks like we have some questions coming in if you want to take a look.
Oh, all right. Okay. So just now some came in. should I implement service mesh now on Istio or Cilium based on eBPF? Which one can you recommend? So I would recommend the Cilium eBPF one. So because it works in accordance with the data path that we have around eBPF, and you don't have the sidecar model there. So there's just you don't have the overhead around that, where you have a sidecar per pod. And in this case, it's just one on the host with an Envoy instance. So it's you save much more on the efficiency side there. And the other thing that is interesting, because I mentioned earlier in the presentation around the L7 use cases that eBPF has, and in this particular case, the SOCMap infrastructure. So this is able to parse into the data that the kernel is pushing out through sockets, and therefore you can parse into L7 and gain observability through that, which we also implement in Cilium. So this is much more efficient than doing this the other way around. All right. So with that, stop sharing, and thanks a lot for your attention.